Welcome. Today we are going to be doing a very sophisticated experiment containing fascinating concepts such as acceleration, air resistance and dropping balls. Here are our balls. We will be dropping our balls from a height of 96 centimeters. Then, using our cutting-edge camera technology, measure the time the ball is in free fall. Then, using this long, complicated Suvat equation, we will determine the acceleration. Of course, most of you watching know that this acceleration is due to gravity, and when doing theoretical physics, we take the value of gravity to be 9.81. However, this ignores air resistance, which will slow down our balls. So which one do you think will be slowed down the most? Let's say hello to our balls. This is our first ball. With a diameter of 16 millimeters, it is the smallest ball we have. Our next ball is orange. This has a diameter of 40 millimeters and is mainly used for a game called ping pong. Our next ball, with a diameter of 55 millimeters, has an arrangement of colours, including my favourite, red. All the way from America, we have an official Major League Baseball with a diameter of 75 millimeters. Our last, largest and most unappealing is our football with a diameter of 195 millimeters. Now we have seen our balls, let's begin the experiment. But first, we must put on our safety equipment, because remember, safety first. This is our first ball, a marble. We will be dropping it from this height 3 times and taking the average in our calculations. So let's drop the ball. 1, 2, 3. Our next ball is a ping pong ball. 1, 2, 3. Our next one is a juggling ball. Let's begin. 1, 2, 3. Our next one is our Major League Baseball. 1, 2, 3. And this is our awful football. Let's begin. 1, 2, 3. Now we've got our measurements, let's work out our acceleration. To work out the acceleration of the marble, we use the Suvat equation, which is S is equal to ut plus half at squared. U, the initial velocity, was 0 in this experiment, and anything multiplied by 0 is 0. So we can actually forget about the first half of this equation, which just leaves S is equal to half at squared. We need to work out A, so we need to make A the subject. To do this, we multiply both sides by 2, which gets us 2s is equal to at squared. And now we divide by t squared, which leaves 2s divided by t squared is equal to a. Now we have made A the subject, we need to substitute the distance and the time. The distance of this experiment was 96 centimetres. However, we need this distance to be in metres. So we divide 96 by 100 to get 0.96 metres. The average time was 0.472 seconds, and we can keep the seconds as it is. So when we substitute the numbers in, we get 2 multiplied by 0.96 divided by 0.472 squared, which is equal to 1.92 divided by 0.222784. This equals 8.618213,157. We're going to round this to 3 decimal places, so we can just say that the acceleration of the marble was equal to 8.618 meters per second to the -2. We followed this method for all the other balls, and here are the results. As we can see, the larger the ball, the slower the acceleration. However, our juggling ball does not follow this trend. This could be for a couple of reasons. One of which could be that the ball was not dropped at the same height as all the others. A way we could make this experiment more accurate was making the distance longer, so the balls would have more time to experience air resistance. I've had very much fun doing this experiment, and I hope you have too. Was it the result you were expecting for? Maybe, maybe not. Let's give a big round of applause to our balls.